Good morning, professors. I'm Alenna and I'll be presenting on credit card fraud detection. Fraud detection is a key challenge in financial security, and my project will evaluate how different models identify fraud while managing accuracy and false positives. This is the table of contents. Credit card fraud causes billions in losses yearly. Fraudsters constantly adapt, making detection a moving target. Severe cost imbalance. Due to only 0.172% of transactions being fraudulent, models struggle to learn fraud patterns. Feature interpretability. PCA transform features limits explainability. Precision recall trade-off. High recall detects more fraud but increases false positives. So to counter this situation, I have handled missing values, removed duplicates, and scaled transaction amounts in data preprocessing. Moving on to class balancing, where I use smooth to make and undersampling to address server imbalance. And then feature engineering, I use random forests for key fraud indicators and created transaction-based features like rolling mean and fraud likelihood. Then I compared classical ML and deep learning techniques, prioritizing AROC, recall, precision, and many other metrics for fraud detection. The last stage is threshold optimization, where I tune decision threshold to balance fraud detection and false positives. So the goals here are actually very simple: to maximize recall to detect fraud effectively, minimize false positives to prevent blocking legitimate transactions, and to develop a scalable and real-time fraud detection model. This dataset saw some Kaggle contained transactions from European cardholders in September 2013 and is widely used for fraud detection research. It contains 284,807 transactions with only 492 fraud cases, highlighting the severe class imbalance. It includes PCA transform features V1 to V28, time elapsed, and transaction amount with inputs with fraud labeled as 1 and normal as 0. On the right-hand side, the class distribution before and after sampling illustrates the extreme class imbalance, which shows the fraud cases are highly underrepresented before applying the balancing techniques. For transaction amount distribution by class, it reveals that fraudulent transactions tend to have lower amounts, which is a key insight for feature engineering. So what we can derive is that fraud detection is challenging due to class imbalance and similarity to normal transactions. Effective detection requires advanced feature engineering and strategic model selection. Now let's go over how we prepare the data for training. We will start off with data cleaning, where I remove missing values and duplicates. I then split the data into 70% training, 15% validation, and 15% testing. This ensures consistent class distribution across all splits. Then for scaling and normalization, whereby I normalize the time features into seconds, transaction amounts were heavily scaled, so I use robust scaler to handle outliers. For feature selection and engineering, I use random forest and correlation analysis to select the key fraud indicators and engineered features such as rolling mean and fraud likelihood. Due to the highly imbalanced dataset, I applied smooth and undersampling. For the charts that you can see on the right-hand side, the feature correlation heat map highlights the strongest fraud predictors. Time versus transaction scatter plot shows the fraud transactions occurs irregularly over time. The top features for fraud detection identifies the key fraud indicators V4, V10, V17. By applying feature engineering and class balancing before splitting, the model learns fraud patterns more effectively and leading to a better fraud detection and reduced bias. For scale and enhanced feature engineering, raw transaction amounts contain extreme outliers which could bias the model. As mentioned previously, using robust scaler, we effectively normalize the distribution. Rolling mean tracks spending behavior over time. Fraud likelihood score estimate risk based on the past fraudulent transactions. Interaction terms captures relationships between existing features. Random forests help identify the most important fraud indicators. Since the dataset had PCA transform features, which is principal component analysis features, consisting of V1 to V28, I retained the most informative components while removing redundancy. This reduced feature correlation and improved training efficiency. Feature importance graph, the random forest, highlights the key fraud indicators like V4, V10, and V14. Threshold matrix curve help to determine the best decision boundary by analyzing recall, precision, and AROC at different thresholds. So, the feature selection and PCA enhance the model efficiency by reducing noise, improving generalization, and preserving the critical fraud patterns. In this slide, we'll compare three classical machine learning models. As she boasts, it has the best recall of 84 detected fraud cases, high AROC of 0.9782, meaning it ranks fraud cases well. However, it has 155 false positives, meaning some normal transactions are wrongly flagged as fraud. Gradient boost is similar to XGBoost with the same recall of 84 detected fraud cases. It has slightly better in terms of precision, which is 0.1342, but at the cost of more false positives of 167. AROC is 0.9770 and remains strong but slightly lower than XGBoost. For KNN, it has lower recall of 79 detected fraud cases, but the highest precision of 0.3591 means that fewer false positives of 52. However, it misses 21 fraud cases, making it unreliable for fraud detection. AROC is 0.9150, which is lower than both XGBoost and Gradient Boost. The performance comparison chart shows that XGBoost has the highest AROC and AUPRC, making it the best model for fraud ranking. For confusion metrics, XGBoost and Gradient Boost both detect 84 fraud cases, but Gradient Boost has more false positives. KNN has the fewest false positives of 52 but also misses the most fraud cases. Thus, XGBoost is the best overall model due to its high recall, AROC, AUPRC, making it the most reliable choice for fraud detection. Gradient Boost will be a good alternative but suffers from more false positives. KNN is certainly not ideal due to high missed fraud cases and weaker fraud ranking ability. I have explored LCM-GIU and hybrid LCM-GIU model to capture the sequential fraud patterns. For LCM, the precision is 0.3333, reflects many transactions as fraud, leading to a high false positive rate. Recall is one which captures all fraud cases but lacks precision. F1 score is 0.5, which is misleadingly high due to predicting all transactions as fraud. AROC is 0.067 and AUPRC is 0.1928, which shows near random performance requiring threshold tuning and better class balancing. The precision recall and ROC curve shows that it performs better than random guessing, but remains weak in fraud detection due to poor fraud ranking and high false positives. For GIU, it is 1 in precision, recall, and F1 score, which reflects all transactions perfectly in the datasets. AROC is 0.97 and similarly for AUPRC, which shows strong fraud ranking but model needs real-world validation to confirm the generalization. So the precision recall and ROC curve on the right shows high fraud detection capability, but there's a risk of overfitting due to perfect scores, so you need real-world testing to confirm the effectiveness. For high performance, the precision is 0.5009 and the recall is 1, F1 score is 0.6673. It misclassifies a large number of normal transactions as fraud. AROC is 0.5038, AUPRC is 0.5016, indicates that model performs no better than random guessing. So this curve actually shows a flat line, indicating that model fails to distinguish fraud from non-fraud cases, so it's completely ineffective, and due to the class imbalance and poor threshold timing. This slide compares classical machine learning models, XGBoost, Gradient Boost, KNN with deep learning models, RCM, GIU, and hybrid RCM-GIU to determine the most effective fraud detection approach. XGBoost is the best overall model, achieving the highest AROC of 0.9782 and AUPRC of 0.7357. It effectively ranks fraud cases while maintaining strong recall, though it has some false positives. GIU performs perfectly in this dataset with AROC of 0.97, AUPRC of 0.97, and 100% accuracy, but this perfect scores might suggest overfitting, so it likely memorized the training data rather than learning the general fraud patterns. Thus, this needs real-world validation for its effectiveness. RCM and hybrid RCM-GIU fail at fraud detection. RCM has poor fraud ranking, AROC 0.067, despite high recall, while hybrid performs at random of AROC 0.5, thus making it completely unreliable. So, the final verdict is that XGBoost is the most practical and reliable fraud detection model. GIU shows the promise but requires real-world testing on imbalanced data. RCM and hybrid models are thus unsuitable due to the weak fraud ranking and unreliable performance. Here are the limitations. Severe class imbalance. Fraud cases are rare, biasing models towards normal transactions. RCM struggled with recall. Hybrid RCM-GIU failed. Small map helps classical models but wasn't effective for deep learning. Next, threshold selection impacts performance. High threshold missed fraud cases and lower threshold improve recall but increase false positives. Dynamic tuning actually is needed for balanced fraud detection. Next is deep learning struggles with structured data. RCM and hybrid models they will underperform versus XGBoost and lack access to raw transaction data using PCA transform features, and it has limited fraud pattern learning causing poor generalization.